Welcome to section 1.2 of the text Elements of Modern Algebra 8th edition by Gilbert and Gilbert. Section 1.2 deals with mappings. Now, the concept of a function or a mapping is fundamental to all areas of mathematics. The basic idea is that correspondences of a certain type exist between elements of two sets. The rule of association between the elements of the two sets is such that for each element in the first set, there is one and only one associated element in the second set. We introduce this concept starting with the definition of a Cartesian product. For two non-empty sets A and B, the Cartesian product is the set of all ordered pairs AB of elements where A is an element of A and B is an element of B. So we define the cross product or the Cartesian product A cross B equals AB. This is an ordered pair. What that means is that AB is not the same as BA. So if you see an ordered pair, that means the little a is from the set A and the little b is from the set B. How do we apply this concept in proofs? Because abstract algebra is all about proofs. In proofs, if we tell you that xy, the ordered pair xy is an element of A cross B, then it means that x comes from A and y from B. And in the other direction, if x is from A and y is from B, then xy is from A cross B. We would use this concept in proofs as we move on with this class. Now let me give you a little example here. If A is the set 1, 2 and B is the set A, B, C, so A cross B is the set of all ordered pairs AB, all ordered pairs, such that A is from A and B is from B. So what would that be? 1A, 1B, 1C, 2A, 2B, 2C. So that is the set of all ordered pairs. Now, interestingly, the cardinality of A is 2 because A has 2 elements. The cardinality of B is 3. B has 3 elements. And the cardinality of A cross B is 1, 2, 3, 4, 5, 6, which is the cardinality of A times the cardinality of B. Question: can we conclude that the cardinality of A cross B always equals the cardinality of A times the cardinality of B? Attempt a proof at that, and we shall discuss that some more in class. 1.2.2 Mapping an image. Let A and B be non-empty sets. Then we define a subset F of A cross B, the Cartesian product, as a mapping from A to B if and only if for every element in A there exists a unique element in B such that the ordered pair AB is in F. Now let me just go down here and break that down a little bit in mathematical notation. So what we are saying is if A is a non-empty set, B is a non-empty set, then we can say F from A to B is a mapping if and only if for every element in A there exists a unique element in B such that B equals F of A. Now we call B or F of A the image of A under the mapping F. So if I pick an element A right here, F of A is the image of A. Now let's talk a little bit about domain, codomain, and range. If F is a mapping from A to B, then A is called the domain, B is called the codomain, and the range of F, C, is the set of all y in B such that y equals f of x for some x in A. Now let's break that down a little bit better. So this is what we have here. If f is a mapping from A to B, A is your domain, B is your codomain. Now the range of f, or the image of the entire set A under f, is defined by f of A equals the set of all B in B such that B equals f of A. Or we could actually break down the definition and simply say this is equal to the set of all f of A such that A is in A. See, f of big A equals the set of all f of little a. So if the set A had three elements, for example, 1, 2, 3, then f of A would be the set f of 1, comma, f of 2, comma, f of 3. Easy. So how do we use this concept in proofs? Now be very careful because some students actually stumble at this point. Playing around with the image of A under F usually poses some problems to some students, but I'm sure it would not for you. So if I say that B is an element of f of A, what does that mean? It means that there exists an element A in A such that B equals f of A. So B, an element of f of A, means there exists an A in A such that B equals f of A. Or if you are proving something with respect to the image, what do you say? Let B be an element of f of A. Then there exists an A in A such that B equals f of A. Very easy, very straightforward. Now, I'm going to use that concept to prove at least one thing before we move forward. It's very important that you actually understand this concept and how to use it in proofs. Let F be a mapping from A to B. Both A and B are non-empty. S1 and S2 are subsets of A. So basically we're looking at the image of S1 union S2, which is the same as the image of A, except that in this case, instead of dealing with A, I'm dealing with subsets of A, S1 and S2. So prove that f of S1 union S2 equals f of S1 union f of S2. Now observe that the right hand side is a set and the left hand side is a set. These are images. So to prove that two sets are equal, what do? We have to verify that they are subsets of each other. So I'm going to pick an element from the left hand side and show that it belongs to the right hand side. Pick an element on the right hand side and show that it belongs to the left hand side, and then conclude that there is equality. Okay, proof. We start off with the forward inclusion. So let B be an element of the left hand side, f of S1 union S2. By definition, what does that mean? It means there exists an element in, just like we had our A, there exists an element in S1 union S2 such that B equals f of A. But A is an element of S1 union S2. What does that mean? By the definition of union, which we saw in section 1.1, A, an element of S1 union S2, implies that A is an element of S1 or A is an element of S2. But if A is an element of S1, then the image of A is an element of the image of S1. And if A is in S2, then the image of A is an element of the image of S2. Or we could simply say hit both sides with the function f. F of A is in f of S1, or f of A is in f of S2. What does that mean from section 1.1? It means f of A is an element of f of S1 union f of S2. But what is f of A? F of A is B. So that means B is an element of f of S1 union f of S2. Hey, wait a minute, where did B come from? B came from f of S1 union S2. Now we have B in f of S1 union f of S2. What does that mean? It means the left-hand side, f of S1 union S2, is a subset of the right-hand side, f of S1 union f of S2, and we call this 1. It's actually beautiful. Now let us look at the reverse inclusion. This time around, let me not use B, let's use Y so that we can see how to play around with Y and X, A, and B. Now, let Y be an element of the right-hand side, f of S1 union f of S2. By section 1.1, what does that mean? It means Y is an element of f of S1, or Y is an element of f of S2. But what does it mean for Y to be an element of f of S1? It means there exists an x1 in S1 such that Y equals f of x1. What does it mean for Y to be an element of f of S2? It means there exists an x2 in S2 such that Y equals f of x2. Common mistake that students make. They would say there exists x in S1 such that Y equals f of x, or there exists x in S2 such that Y equals f of x. S1 and S2 may not be the same set, so we cannot say x in S1 and x in S2. So we have to customize, if I may use that word. So in particular, we have x1, an element of S1, implies that x1 is an element of S1 union S2. If I hit f on both sides, I end up with f of x1, an element of f of S1 union S2. But what is f of x1? F of x1 is y. So that simply means that y is an element of f of S1 union S2. But recall, this here is the left-hand side. So we picked an element in the right-hand side, and we have shown that the same element exists in the left-hand side. What does that mean? It means the right-hand side is a subset of the left-hand side, and we call that 2. 1 and 2 implies equality, and we're done. Okay, let's visit the concept of inverse images and then conclude the first part of our lecture from section 1.2. Review. If F is a set from A to B, A and B non-empty, and S is a subset of A, then the image of S is simply the set of all elements Y in B such that Y equals f of x. And then we can also define the inverse image. Now let's break that down some more. Let F be a mapping from A to B, where A and B are not empty, of course. And let S be a subset of A, and let T be a subset of B. I'm going to give you two definitions here. Number one, the image of S under F. we've seen that before, is simply going to be the set of all elements y in B such that y equals f of x, or simply the set of all f of x such that x is an element of S. Now, define the inverse image of T. Remember, T is a subset of B. Let's go back up here. F is a mapping from A to B. T is a subset of B. The inverse of F goes from B back to A. So, the inverse image of T is the set of all elements x in A such that f of x is an element in T. Watch this very carefully. It's actually a very beautiful definition. You can prove with this a lot easier than dealing with the image. That is the beauty of the inverse image. So f inverse of T equals the set of all x in A such that f of x is an element in T. Now let's see how we can apply these in proofs very quickly. For the first one, the image, we've done that already, but repetition is the mother of learning. So y, an element of f of s, if and only if there exists an x in S such that y equals f of x. Now, this is the new thing. X is an element of f inverse of T if and only if f of x is an element of T. Observe how easy this is. Basically, this is f inverse. It's like we're taking f inverse from the right-hand side to the left-hand side of this inclusion sign, and if it goes over to the left-hand side, it becomes f. It comes to the right-hand side, it becomes inverse. As easy as that. It's just like x squared equals 4. If I move the squared over to the right-hand side, it becomes square root. It's a very easy concept. I'm going to give you a problem using this concept. Example, let f be a mapping from A to B, both A and B non-empty, and let T1 and T2 be subsets of B. I want you to prove that f inverse of T1 union T2 equals f inverse of T1 union f inverse of T2. These are sets. How do we prove that two sets are equal? We prove that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. So I'm going to pick an element in the left-hand side and show that it definitely belongs to the right-hand side. Forward inclusion. I pick an element from the right-hand side and show that it belongs to the left-hand side. Reverse inclusion, and then we can conclude equality. Let x be an element, that is the forward inclusion. Let x be an element of f inverse of T1 union T2. Then, remember, f inverse moves from the right-hand side to the left-hand side, it becomes f. Then f of x is an element of T1 union T2. From section 1.1, what does that mean? It means f of x is an element of T1 or f of x is an element of T2. Now, let me pause very quickly and mention this. We are using the inverse of f here because the question clearly shows that f inverse exists. You would not be asked to solve problems with respect to the inverse image if the inverse of f did not exist. So we can use it freely. Okay. So x, an element of f inverse of T1 union T2, what does that mean? It means f of x is an element of T1 union T2. Again, that means f of x is an element of T1 or f of x is an element of T2. We are free to use the inverse of f So we can move F back to the right-hand side. X becomes an element of F inverse of T1. Just move your F back to the right-hand side, if we could say it that way. Or X is an element of F inverse of T2. But if X is an element of this set, or X is an element of this set, then from section 1.1, X is an element of the union of both inverse images. We started off with the left-hand side and see where we are in the right-hand side. What does that mean? This means that the left-hand side is a subset of the right-hand side. F inverse of T1 union T2 is a subset of F inverse of T1 union F inverse of T2, and we call that 1. The reverse inclusion. So pick an element X from F inverse of T1 union F inverse of T2. What does that mean? From section 1.1, I have my union here. That means X is an element of F inverse of T1, or X is an element of F inverse of T2. Now I have them apart, and I can use the idea that the inverse of F exists, and I can move my F inverse over. So X an element of F inverse of T1. What does that mean? F inverse moves over, it becomes F. So that means F of X is an element of T1, or F of X is an element of T2. F of X, T1, or F of X in T2 from section 1.1. What does that mean with the word or? It means F of X is an element of T1 union T2. F inverse exists, so I can move my F back to the right-hand side of the inclusion sign, and that means X is an element of F inverse of T1 union T2. Oh, exciting. We picked our X from the right-hand side. We have now shown that that same X is in the left-hand side. So that means the right-hand side F inverse of T1 union F inverse of T2 is a subset of the left-hand side F inverse of T1 union T2, and we call that 2. This was 1. This was 1 right here. The left-hand side is subset of the right-hand side. This is 2. The right-hand side is subset of the left-hand side. And 1 and 2 implies equality, and we are done. This will be the end of the first part of the lectures from section 1.2. Watch out for the second part of the lectures from 1.2. Thank you.